All right, so let's begin talking about subspaces. So let's say that we have a vector space V. Okay. All right, and then let's say that we have a subset W of V. So W is a subspace of V if W itself is a vector space. So it's kind of a simple definition, I suppose. Okay. Okay, so to check if something is a subspace, you actually don't need to check all those properties of a vector space. Yeah. So to be it, well, no, that's true though. Yeah. So actually, okay. No, I see. I see. Yeah. Yeah. Well, so first, every vector space is considered a subspace of itself. Okay. Just sort of by this definition. Now in this case, so for W to be a subspace of V, it had to be a subset of V to begin with. So say like if V was like larger than W, uh, then like V would not be a subset of W. That's why you couldn't say that V was a subspace of W because of that. Okay. Yeah. So yeah, so a subspace has to first be a subset of the vector space, and then in addition to being a subset, it has to have those properties of a vector space, right? Now, if you're checking if something is a subspace, it turns out you don't have to check all of those properties of a vector space. There's only two of them that you have to check, okay? So I'll kind of state that within a theorem right now. So still the same context, W being a subset of a vector space V. So this theorem says that W is going to be a subspace of V if and only if so first W has to be closed under addition. And so what does it mean to be closed in addition? So remember that means that if, let's say W1, W2 are two vectors in V, sorry, in W, then their sum, W1 plus W2, must also be in W. Okay. So take two vectors in W, the sum is also in W. That's what it means to be closed under addition. And then to be a subspace, it also needs to be closed under scalar multiplication. Okay. And then just a reminder of what it means to be closed under scalar multiplication. So if C is any scalar, and if W1 is any vector in W, then the scalar multiple C times W must also be in W. Okay. Oh, maybe I said W1, so I'll do W1. All right. Okay. Yeah, so then to check if something is a subspace, you only have these two properties that you need to check. So I'll maybe do a couple of examples, just like checking whether a given subset of a vector space, is a subspace or not. Okay. So maybe to start with, let's take R3. So R3 is going to be our vector space B. And then I'm going to define a set W. So W is going to be the set of all vectors x, y, z in R3, okay, such that, let's make up some numbers. So let's see, 2x minus y plus 3z is equal to 0. Okay. So it's a specific subset of R3. So W consists of the vectors which satisfy this equation. And we want to check if this set W is a subspace of R3 or not. Okay. Okay, so in order to do that, we'll go through the two properties. So let's start by checking to see if W is closed under addition. Okay. So here's how that will work. So to be closed under addition, any two vectors in the set, the sum must also be in the set. So what we're going to do is we're going to start with two vectors in W. So I'll just call them W1 and W2. And let's say the components of W1 are x1, y1, z1, while the components of W2 would be x2, y2, z2. Okay. And I'm assuming that these two vectors are in the set W. And in this specific problem, that means that these two vectors must satisfy this equation. So we don't know the numbers x1, y1, z1 exactly, but we do know that those numbers satisfy this equation. Since we're assuming that W1 belongs to W. And then likewise, the components of W2 also satisfy this equation as well. Okay. So all of this I've written down right now. This is one of our assumptions going into this part of the problem. Now what we need to do is we need to check if the sum of these two vectors will also be in W. So the first thing we should do then is we should add our two vectors together. So let's just add W1 plus W2. And of course, when we add them, it's just adding the x, y, and z components together. Okay. All right, so that's what the sum will turn out to be. And then to check whether this new vector that we have here, the sum, to check if this is in W, we need to check whether it would be a solution to this equation that defines W. Okay, so here, let me kind of mark the, oh, that didn't work. Let me try to change colors again. Okay. So here, let me mark the x, y, and z components kind of more clearly like that. So since we're checking to see if the sum satisfies this equation, let me start by just plugging these x, y, z components into the left-hand side of this equation. So we're going to have like 2x, and then we're going to have minus y, then we're going to have plus 3z. And so the question is, is this going to equal 0? Okay. Now we don't know these numbers, but we do have this assumption that x1, y1, z1 satisfy this equation, and that likewise x2, y2, z2 satisfy this equation as well. So what we can do here is, let's say if we distribute both sides of this, or if we just distribute everything out, you're going to get 2x1 plus 2x2. You're going to get a minus y1 and a minus y2. And you're going to get a plus 3z1 and a plus 3z2. Okay. Yeah. So the left-hand side, you can rewrite it like this, and then using our assumption up here, each of those terms in parentheses is equal to 0. So this is really like 0 plus 0. So then we do have that everything is equal to 0, okay? And so that proves that the set W is closed under addition right now then, okay? So the sum is also in W, and therefore you can say W is closed under addition. Okay. Now that's not enough to conclude that W is a subspace though. So to prove that W is a subspace, you have to also show that it's closed under scalar multiplication. So we'll take a look at that part next. Okay. So for scalar multiplication, you want to take a vector in W, multiply it by a scalar, and then argue whether or not that multiple is in W or not, okay? So let me continue working with W1 from this first part. And since I'm checking closure under scalar multiplication, let's multiply W1 by a scalar C. So multiplying by C will just multiply each component of W1 by C. And now the question is, is this vector going to be in W? Okay. So to check if it's in W, again, you want to check whether the components will satisfy the defining equation for W. So if we take the X component, the Y component, and the Z component, we plug those into the left-hand side of this equation. Okay. We want to check, is this going to be 0 or not? And in this case, what we can do is the C, we can actually factor it out of all three terms. That will leave us with 2x1 minus y1 plus 3z1. And using our assumption up here in blue that w1 was a vector in W, we have that this expression in parentheses is equal to 0. So therefore we have like C times 0, which then of course is equal to 0, okay? So this shows us that any scalar multiple of a vector in W is also going to be in W, since it satisfies the defining equation. And therefore, you can make the conclusion that W is also closed under scalar multiplication. So finally, since it's closed under both addition and scalar multiplication, we can say that W is in fact a subspace of R3. Okay. Okay, so that's kind of one example of just kind of looking at how you would show that something is closed under addition and then closed under scalar multiplication. Okay. Before I go on to a brand new example, I just wanted to make sort of an observation. So let's say that I were to change this example slightly. Okay. So in this example, W was the set of vectors in R3, satisfying 2x minus y plus 3z equal to 0. So I just wanted to take a look and see what would happen if instead of equaling 0, what if I had it set equal to some other number? Say, for example, if I had it set equal to 1 up there. So how would that change the problem if we now had 2x minus y plus 3z equal to 1 rather than 0? Mm-hmm. Let's see. Yeah, okay. So if we kind of go through the process again, so we start with two vectors in W. Now this time, what it would mean to be in W then, it would mean that each of these were equal to 1 rather than 0. Okay. And we would add our two vectors together. We would plug the components into the left-hand side of this equation. Now, rather than checking to see if it's equal to 0, we'd be checking to see if it was equal to 1 this time, okay? And when we distribute all the numbers and group everything like this, well, over here, this assumption now says that each of these are equal to 1. So instead of getting 0 plus 0, we'd actually get 1 plus 1 at this point, which would leave us with a right-hand side being equal to 2, okay? So in other words, it does not equal 1 when we add them up. Instead, it equals 2 now. And so because it's not equal to 1, that would prove in this case that W was not closed under addition. And then if it's not closed under addition, you can already say that it's not going to be a subspace then. And you don't even need to check the scalar multiplication, okay? All right, so that's kind of good to note that changing the 0 to a 1 makes it no longer a subspace. I'll do maybe another example of checking whether something is a subspace or not. Okay. I'll do another example in R3. I'll do a quick one first. So let's say I'm looking in R3 once again, and this time I'm going to define W to be the set of all vectors x, y, z in R3, such that x squared plus y squared plus z squared is less than or equal to 1. Okay. So I think you guys would probably recognize W as being the unit ball in 3 dimensions. Okay. Right. So this is what our set W looks like this time. And we just want to argue whether or not W is going to be a subspace. Okay, so in this case, W is not going to be a subspace, all right? There's many different arguments for why it would not be a subspace. Let me kind of give like a visual argument first. So, here's a vector that's inside of W because it's within the unit ball. Let's call this vector V for the moment. So if W were a subspace, it would have to be closed under scalar multiplication. Meaning if I were to take this vector V and if I were to multiply it by a scalar, for example, if I multiply it by 2, then that result would have to be in my space still, okay? But in this case, in this picture, you can see that 2V is no longer inside of W. So we have just sort of like a pretty easy to see example of a vector in W whose scalar multiple is not in W anymore. Okay. So that's kind of a short argument that W is not closed under scalar multiplication. And that would already allow you to conclude that W is not a subspace, okay? So aside from doing kind of a visual example, like how I did here, if you're going to show that something is not a subspace, you can also use like specific numbers to give like a counter example. So just to kind of illustrate how that would work, and maybe here what I would do is I would take 2 vectors that are in W. So they have to be vectors in the unit ball. Let's just pick some obvious ones like 1, 0, 0. That's definitely in the unit ball. W2, let's take it to be maybe like 0, 1, 0. So again, definitely in the unit ball. When we add them, you get the vector 1, 1, 0. And if we take the x, y, z components of the sum, and we do like x squared plus y squared plus z squared, in this case, you're going to get an answer of 2, which is not less than or equal to 1. So maybe I'll write it like that, not less than or equal to 1. So therefore, the sum is no longer inside of W. So that this would show that W is not closed under addition either, okay? Okay. So kind of the point that I want to make is if you're showing that something's not a subspace, it is enough to just provide like an example showing that one of the two conditions will fail. So you can use specific numbers if you're just going to provide an example like that. But in contrast, if you want to show that something is a subspace, it's not enough to just look at a single example. Because to be a subspace, say that to be closed under addition then, it has to be that for any two vectors in your space, their sum will also be in the space as well. So therefore, to make an argument about like any two vectors in your set, you have to keep it kind of arbitrary like we did up here in the first example. And so here I couldn't use numbers, I had to use like kind of variables instead for that, okay? All right, any questions? Okay. Maybe I'm just gonna do like one more example. So I did an example like in R3, but let's do another example, but in a different vector space. So let's consider the space of 2 by 2 matrices. So I'll use a M2 to denote that. The vector space of 2 by 2 matrices. Okay. And then I'm going to single out a certain subset of M2. So let's say that W is going to be the set of all matrices A, B, C, D. So in M2, such that I have a couple of examples you can do. Actually, I'll tell you what, let me do a different example because I have quite a few examples and I'm trying to think which one I want to do. I'll do a different one, okay? So instead of M2, let me do just an example in Mn. So this is the vector space of n by n matrices. And in this case, I'll have W be the set of all n by n skew symmetric, or sometimes this is known as anti-symmetric as well. Okay. And so I know you guys have talked about symmetric matrices. I'm not sure if you guys have at least heard of the anti-symmetric matrices. So just in case you guys aren't familiar with it, I'll define it real quick. So to say that A is a skew symmetric matrix, the definition of that, what was that? Sorry, I can't hear you. Okay, yeah. So the definition of skew symmetric means that its transpose is equal to the negative of the original matrix. Okay. So if you remember the definition of being symmetric was that the transpose of the matrix is equal to itself. Okay. So symmetric means A transpose equals A. So when you have the condition that A transpose is negative A, they call that skew symmetric or anti-symmetric. Okay. So if we're looking at the set of all n by n skew symmetric or anti-symmetric matrices, we want to check if this is going to be a subspace of the space of all n by n matrices. Okay. No, go ahead. Yeah. Yeah, so we'll look at an example, yes. So to see like what a skew symmetric matrix looks like real quick. Okay, so you guys have probably seen that for a matrix to be symmetric, that it has to be kind of symmetric across the diagonal. Okay, so you guys have seen that for a matrix to be symmetric, it has to be like symmetric across the diagonal. So for skew symmetric, instead of being the same across the diagonal, it has to be like the negative across the diagonal instead. Okay. And in addition, for the diagonal entries, for skew symmetric matrices, the diagonal entries, they have to be equal to 0. Okay. So this is what a skew symmetric is going to look like. You can kind of verify if you do the transpose of this matrix. So if you take like the rows and you write them as columns now, so you can see in this case how A transpose is equal to the negative of A. Okay. So that's kind of what a typical skew symmetric matrix looks like. All right. Yeah, that's right. So I don't think you guys would do too much for skew symmetric matrices. They might come up in like a question or two perhaps, but symmetric matrices I think are kind of more important for you guys in this class. So one of the like major theorems that you learn at the very end of the semester kind of concerns symmetric matrices. So for skew symmetric, there's not as many like major theorems, so that there's many like special properties of them for sure, and they do come up in like some applications, of course. Okay. All right. Now, for this problem, we want to check if W is a subspace of Mn. So here, if you want to check like the closure under addition, since we're dealing with like n by n matrices, it's maybe a little bit hard to like write out like an n by n matrix, and like maybe you want to try to like write out two n by n skew symmetric matrices and add them up and see if the sum is still skew symmetric, because that's what you'd want to do to check closure under addition. But since it's like n by n, that's kind of hard to do. So I just kind of wanted to show like how you can maybe answer it without like trying to write out what the matrices look like. Okay. So the key is that we're going to be using this definition of a skew symmetric matrix to try to verify the two properties. Okay. So let's say we want to check if it's closed under addition. So we would suppose that if we have two n by n matrices A and B, which are skew symmetric. Okay. So therefore, we know that A transpose will be equal to negative A, and we also know that B transpose will be equal to negative B. Okay. When we add our two matrices together, we want to check is the sum going to be skew symmetric or not. So the way that we're going to verify that is, well, to be skew symmetric, its transpose would have to equal the negative of itself. Okay. So if we try to transpose the sum right now, what we can do is we can use some properties of the transpose operation. So when you transpose a sum, you can distribute the transpose to each term. Okay. And then here we have the assumption that A and B are skew symmetric. So therefore, we are assuming that A transpose is equal to A, or sorry, that A transpose is equal to negative A, and that B transpose is equal to negative B. Okay. So when we kind of put 2 and 2 together, we see that the transpose of A plus B turns out to be the negative of A plus B, so minus A minus B. Right, okay. So yeah, so that shows us that the sum is in fact skew symmetric. Its transpose is the negative of itself. And so therefore, you can make the conclusion right now that W is closed under addition. And then just to check the second property, so let's say that we take A, which is skew symmetric, and we multiply it by a scalar. So we need to ask, is the scalar multiple now also skew symmetric? So we're going to take CA, we're just going to transpose it. And I guess like a property of transpose is that you can basically pull the constant outside. So it's the same as C times A transpose. And then again, we're assuming that A is a skew symmetric matrix. So that A transpose is going to equal negative A. So C times minus A, which you can always write as minus CA. Okay. So again, we see that the transpose of CA is the negative of itself. And that proves that CA is also skew symmetric then. Okay. So therefore, it's also closed under scalar multiplication. And so since it's closed under both addition and scalar multiplication, that proves that W is a subspace of Mn, okay? So the set of all n by n skew symmetric matrices does form a subspace, okay? Good. So I think there was a homework problem about symmetric matrices. So you can prove that symmetric matrices are symmetric along the same lines as what we did in this example, okay? So I'll just wrap up this kind of part of my review by just like listing some examples of subspaces. So in R2, so for R2, we kind of can give like a complete list of all of its subspaces. Okay, so if we take the set consisting only of the zero vector, that is always a subspace because it's always closed under addition and scalar multiplication. In addition to the origin, any line that passes through the origin is also going to be a subspace of R2. And then like R2 itself is a subspace of itself. So I kind of mentioned that earlier. I guess for any vector space, the zero vector by itself and the space itself, those two will always be subspaces. Okay. And R3, there's kind of something kind of similar that you can say. So the subspaces would be like the zero vector by itself, lines through the origin. And R3, any plane that passes through the origin will also be a subspace now. And then of course like R3 itself. Okay. So here, we'll talk about dimension later this semester, maybe in 2 or 3 weeks if I had to guess. But I guess like here there's some intuition that like the origin by itself is just a point, so it's kind of like 0-dimensional. Lines are 1-dimensional, and R2 is 2-dimensional. So then here we've got like a 0-dimensional subspace. Lines through the origin are the 1-dimensional subspaces. Yeah, so like 0-dimensional is basically just going to be the origin by itself, so it's just a point. It has no like length or area or volume or anything like that. Yeah, it has one vector in it, but only one. Okay. That's right. Yeah. So there's one vector there, the zero vector. Okay. Planes through the origin would be like the 2-dimensional subspaces of R3, and then the only 3-dimensional subspace of R3 is itself. And you can maybe guess like you're not going to have any 4-dimensional spaces in R3 because you wouldn't be able to fit it in there. Okay. So you can kind of generalize this to like Rn. The like 1-dimensional subspaces would be lines through the origin. 2-dimensional subspaces would be planes through the origin. And then you can have like these sort of like k-dimensional planes, if you will, through the origin would be like the k-dimensional subspaces and so forth. If we look at like a space of n by n matrices, Mn, so just some examples of like subspaces. So the set of all like n by n upper triangular matrices would form a subspace. It's closed under addition because the sum of any two upper triangular matrices is also upper triangular. And it's closed under scalar multiplication because if you multiply an upper triangular by a scalar, the result is still upper triangular. Yeah, okay. The same argument works for n by n lower triangular matrices. That set will also constitute a subspace. The n by n diagonal matrices. So the sum of any two diagonal matrices is also diagonal. And the scalar multiple of a diagonal matrix is also diagonal. Remember that diagonal matrices are matrices that have 0 everywhere except for the diagonal. Okay, so just in case you guys don't remember that. We already mentioned skew symmetric matrices, and I also mentioned that it holds for n by n symmetric. Okay. So those are some of the examples of subspaces. There are more, of course, but these are just like kind of the ones that I'll highlight. The sort of example that I feel like I see a lot of regarding like spaces of matrices or like whether something is a subspace or not regarding matrices. If you take the set of all like n by n invertible matrices, this is not going to be a subspace. A simple example for why that would be the case is that it's not going to be closed under scalar multiplication. So to understand that, let's just look at an example. So let me take the identity matrix, which is definitely invertible. And let's say I multiply it by a scalar, in particular if I multiply it by the scalar 0. Okay. Well, of course, that will produce a 0 matrix, which is not invertible. Yeah, 0 matrix is not invertible in terms of like multiplication, right? Remember, invertible means the product equals the identity. And 0, of course, when you multiply, will give you 0. Yeah, okay. Okay. So that proves that's not closed under scalar multiplication with this kind of example here, okay? Yeah, okay. If I take the n by n, like non-invertible matrices, it's also not a subspace. So just kind of like a short example of why that would be the case. You can take two matrices which are not invertible, but will add to produce an invertible matrix. So these two matrices here are not invertible because they have a row or a column of zeros. But their sum is the identity matrix, which is invertible, okay? So that shows that it's not closed under addition, and that's why it's not a subspace. Okay, geez, that was a lot of work. Let's see here. Okay, so I'm going to move on, sort of. So I'm going to talk about a new topic. I'm going to talk about the notion of span. Span. Yeah. Which we've kind of talked about in the past, but I guess we're just talking about it again in like this context of like vector spaces in general. So let's say that we have a collection of vectors v1, v2, maybe like up to vk. Let's say that these are vectors in some vector space V. Okay. So a linear combination of these vectors, just as before, a linear combination will simply be any like sum of scalar multiples of the given vectors. Okay. And then the span of a collection of vectors will be defined to be the set of all the linear combinations of the vectors v1 through vk. Okay. This is the definition here. All right. So the span of a collection of vectors will always be a subspace of like the space that they were in. Okay. Span of v1 through vk is going to be a subspace of v. Essentially, if it contains all the linear combinations, it's going to contain all the sums, so it'll be closed under addition. And it'll contain all the scalar multiples, so it'll be closed under scalar multiplication. Okay. Yeah. Mm-hmm, mm-hmm. So a subspace has to be closed under addition and scalar multiplication. And I guess like a span in particular will always be a subspace because it'll always satisfy those two properties. Okay. So that's a very good question. In a sense, every subspace is also the span of some vectors that are inside of it, though. Okay. That's right. There are different concepts, though. So kind of like as an example, so I kind of said earlier when I was giving a list of subspaces that like a 2 by 2 upper triangular matrices. I said that this would be a subspace the space of all 2 by 2 matrices because it's closed under addition and it's also closed under scalar multiplication. Yeah. Now it is also the span of a certain of like sum of matrices, if you will. So kind of the simplest way to get like a spanning set, if you will. If I take this sort of generic 3 by 3 upper triangular matrix, notice that you can write it as a linear combination of like 3 specific upper triangular matrices. Okay. Okay, so here we see that if you take the set of all linear combinations of these 3 matrices, that will produce the set of all upper triangular matrices. Okay. So therefore, these 3 matrices, 3 upper triangular matrices, span the space of 2 by 2 upper triangular matrices. And I guess like for any subspace that you give me, or just like for any subspace that you choose, in theory, you can find some vectors in that space which will span the entirety of it. Okay. So in that sense, every subspace is the span of some vectors. Okay. So and they're sort of equivalent in that sense then. But nevertheless, we'll consider them different concepts as well, though. Okay. All right. Good. Yeah, very good question. And let's see here. Let me try to do maybe an example involving span right now. So in this example, it was maybe a little bit clear that these 3 matrices will span the space of all 2 by 2 upper triangular matrices. We've done some examples like this in the past, but I just wanted to kind of bring it up again right now. But let's say that I have some vectors in R3. Let's call them V1, V2, and maybe V3. Okay. And let's say we want to check that these 3 vectors will span R3. All right, so how could we approach this problem? There's a couple of ways you can think about it. Okay. But the way that I'm going to set this one up is, so to check that these 3 vectors span R3, that's asking is any vector in R3 a linear combination of these 3 vectors? So to check if that's the case, what I'll do is I'll form a combination V1, V2, and V3. And I want to see, is it possible to produce any vector in R3 using these three vectors v1, v2, v3. So because I want to check if it works for any vector, notice that over here I'm actually using like letters A, B, C for the right-hand side rather than like using any specific numbers. Okay. And so here, this will give you like a system of equations, and we want to see if we can solve for x, y, and z. Okay. So in this case, let me set up the augmented matrix real quick. And let's start trying to solve to see if we can find a solution or not. So here we'd start doing elimination. We'd probably start with row 2 minus 2 row 1. So when we do row 2 minus 2 row 1, that's a 0. No, that's not a 0. That's a 1 minus 4 is negative 3. Here we would technically do b minus 2a. Okay. All right. And next, let me simplify this a little bit. So I think what I'll do is I'll maybe multiply row 2 by 1/3 to get rid of those 3's, or just to simplify them. And maybe I'll multiply row 3 by 1/2 as well. I think that'll look nice. And notice here that if we did add row 2 to row 3, so row 3 plus row 2, we get this row of zeros at the bottom. And let me just kind of note what's on the right-hand side as well. So we're adding row 2 to row 3, so it would be 1/2 c plus 1/3 b minus 2a. So when we get to this point, notice that on the last row, the last row gives us the equation like 0x plus 0y plus 0z equals everything over here on the right. And so clearly there's not going to be a solution for all the possible values of a, b, c. So here I'll maybe say that the solution does not exist for all possible a, b, c. So therefore, these three vectors v1, v2, v3, they would not span R3. Okay. Now, we could actually be maybe a little bit more specific. So we see that a solution would only exist when the right-hand side of this equation is equal to 0. So that tells us some information that a vector ABC will be in the span of our three vectors if and only if this expression that we had on the right is equal to 0. Because if this were 0, that equation would be consistent. 0 equals 0. All right, so then here, whoops. So if and only if this equals 0. So this is kind of like a condition that a vector would have to satisfy in order to be in the span of these 3 vectors. Okay. But let's see here. I guess it's past 12:15 now. All right. So yeah, I don't know. Maybe I'll try to. Should I continue? I mean, you can leave now if you need to. Let me think if I want to squeeze in like one more example. Yeah, sounds good. Okay. Hmm. Yeah. Yeah, I think I'll end my review here as well. And I'll just resume next time. All right.